thank you. Welcome for coming to my talk, and thanks also for the organizers to invite me to give this talk. And also thanks for the sponsors for making this possible. I was in great company at lunch. They asked me, what's your talk about? So I gave them our elevator pitch. It was a bad one because one of the replies was, well, I don't get the great strokes of the big line of your talk. So I'm going to start up front by telling you so you can spot it when it comes flying past. So every day, I, and probably you as well, work behind a computer, program it, tell it to do what you want it to do. But not very often do I stop and think, well, what's a computation actually, and where does this come from? And it's a lot about the stuff Avdi talked about this morning, like sharing your moment of awe. And in my sense, I'm a mathematician, I'm going to tell you that in a minute. Computations is a very intimate thing, and there are a lot of aspects of computations, and I want to share one frivolous aspect to you today. So this talk is going to be a bit about the theory of programming. There's a lot of Ruby in it, but hopefully it's enjoyable. So let's see if this is working. It's not. This is a shame. So this is my treasure map for my talk. First, you have to head south to the introduction, then take 100 paces to the left to the crisis, which will avert via Alan Turing, which is a major figure in this talk. I'm going to talk a bit about complexity, what that means, and what's the role with computations. And then we're going to discuss alternatives, in particular, a playful alternative. If at any moment you want to ask me questions, just draw my attention, and if I'm not thunderstruck, then I'll try to answer your question. So, who am I? I'm Daan van Berkel. Foremost, I'm a husband and a father for Sophie. This is my daughter. I hope she will enjoy the computer as much as I do, because, well, I think it's a wonderful machine. I work for a company, Luminous. Actually, this is the logo. My boss wanted me to show it, so this is the only time I'm really going to do that. So I earn my pay, I guess. And I study mathematics, like I told you. Mathematics is a very interesting subject, but also very bit dry. So I'm going to hope to liven it up a bit today. So when I checked various information channels on the ArrrrCamp, I thought, well, I've got this. ArrrrCamp is in Belgium. I know a famous Belgian pirate. It's Pirate Pete. So I watch this with my daughter all the time. So I really was focused on doing this right. So I even bought a teddy bear. And then I checked my Twitter stream again, and I saw this. Like, what? Booze? Pirate Pete doesn't drink. So I was like in tears calling the captain. What should I do? I prepared a different talk, but he assured me that everybody in this room will like play and games. So I'm hoping this will go okay. If not, just go for the booze afterwards. So I'm a mathematician, and mathematicians are a bit of the odd one out, actually. So they have a very strange opinion of what their science is. This comic will pick that. Mathematicians think they're the purest science there is. Well, they're right, obviously, because they're mathematicians. But what's interesting about these mathematicians is that apart from the other sciences, they actually don't talk about worldly things. They cock up a new world in their mind and reason about that, which is very fun for the mathematicians. But they can get a bit of a pride and strong-headed about their ideas. They might get the idea that there's some sort of God holding up the universe in their head. So it's good to take these mathematical views and turn them upside down and take them on their word and use that word against them. And one person who did that was Bertrand Russell. And Bertrand Russell was a famous philosopher and mathematician. And what he did, he asked the question to the mathematicians along the lines of this. So think of a set. a naive set, if you will, a set like you could use in Ruby. But actually this set is far more powerful because it can hold infinite amount of stuff, things. And he asked, so take a set of all the things that do not contain themselves. So all the mathematicians went into their studies, start scribbling, yeah, okay, we've got this. And then he asked, does S contain itself? So we're a group of smart people, so let's think about that. Okay, so let's assume that S contains itself. So by the very definition of S should not be in itself. So wait, so S cannot be in itself. So let's assume S is not in itself, but by the very, I should have prepared this slide a bit more, I guess. So S can't exist, actually. And that's very disturbing for a mathematician, because all the mathematics up to that moment was built up of sets. So if you can imagine a set that doesn't exist, why would you imagine the other sets that are tame do exist? So this was a very, very deep crisis in mathematics, and Bertrand Russell did that for us. So, haha, mathematicians. Unfortunately, there was another mathematician that said, okay, settle down, I'm going to solve this problem, let's just formalize mathematics. Let's just manipulate symbols like a computer does, actually, and extract meaning only for the end result. This was David Hilbert, and Hilbert made a program, actually, not a computer program, but a plan to formalize mathematics. And he was a bit of a captain, actually, of the mathematical community at the time, because his crewmates just executed his plan. The only question that remained was how? How do you formalize this mathematics such that these type of freak sets that shouldn't be able to be described shouldn't exist? Well, it gets a bit interesting now, because we're in the beginning of the last century, and along came a very handsome man named Alan Turing. So Alan Turing was a Brit. He was a mathematician as well. And what he did was he dreamed up a machine to formalize computation. And this is actually the basis of modern computers. So I'm gonna zoom in the ideas that Alan Turing provided us to describe computations. So who knows what the first computer was? Nobody. Well, sorry? Yeah, that's actually the correct answer. So I hoped that some would say, well, it would be the ENIAC, which was built by the Americans, but that's actually wrong, because the British built a computer along the lines of the ideas that Turing fed them, but it was classified, so they couldn't tell about the computer until it was declassified only a few years back, and it became clear that the British were actually the first to build a real computer. And the interesting stuff is that Alan Turing worked at Bletchley Park, and in Bletchley Park there is the actual working computer that he built to crack the Enigma code. So if you want to remember one thing from this talk, it's go to Bletchley Park and visit that museum. So what did Alan Turing do? He invented a machine, and the machine in itself was very simple. There's an infinite amount of tape to the left and right. You can write symbols into that tape, and you can read them. And depending on the state in which the machine is, which is symbolized with a little gray circle, it decides what to do next. So it could either write a new symbol and move to the right or to the left of the tape and go into the next state. So I'm going to simulate this Turing machine by clicking on this button. So it has two sets of symbols on this tape, which represent numbers. And 0 is a very important number, so you have to count 0, 1, 2. So the first numbers represented is 2, and the next will be 3. And this program, if it worked correctly, will calculate the sum of these two numbers. So to visualize what the Turing machine can do, let's step through it. So in this state, it's going to read a 1, or a dash. It's going to determine, okay, I'm going to write a dash, so there will be a dash left, and I'm going to move to the right. So after one step, this is the situation. Oh, I told a lie. It's going to write an X. So it's going to write an X. That's now in state 2, T2. And in this state, it's going to read the dash. It's going to write an X. This time, I know it for sure. It's going to move to the right. Because what it's going to do is going to add 1 to the other number. So now it will travel to the number at the end, append the 1, so we're going to do that right now, and travel back. So this is very tedious, so it can do that automatically. So what this Turing machine does is it's very simple to describe. It will look at a symbol on the tape, it will interpret in which state it is, it will combine the two to figure out what to do. We'll do that, and then it's done for one step. And by constantly doing that over and over and over again, it can compute this thing. So what we're going to do now is clean up the tape. So it has already computed the answer, but it doesn't know that yet. And it's going to shift the answer so that the input arguments, so to speak, are erased, and that the only remaining part is the answer. And it will stop, and when it will stop, the answer is pointed out by the hat. So he's a bit busy, isn't he, our little friend? And eventually it will stop, right about now. And if you count from 0, 1, 2, 3, 4, 5, you know that the Turing machine computed the sum of 2 and 3. So I think this is a round of applause for the Turing machine. Yay! Woo. So this isn't all that Alan Turing did. He did some fancy work by describing what Turing machines can do, and this is very interesting. But actually, the basis is just this: tell a simple machine what to do every step. And if you look at the Turing machine program, it's nothing more than a tedious long list of if you're in this state and you're reading this symbol, go into that state, move to the right, and write that other symbol that I'm going to do. And this is actually the actual program that the Turing machine is using to calculate any sum of two numbers. But it's slow. It's like even slower than the Commodore 64 I used to play with. And why is that? Why is it so slow to begin with? And is this something inherent to the problem, or is it something that can be sped up? Well, I'm going to draw a picture with this marvelous tool called a drawing tool, and try to explain that there are certain classes of problems in which the Turing machine is actually relatively fast, although it's slow in our terms. And that's because that's the problem of describing a collection of problems called P. Does anybody know what P stands for? No, it's actually pirate. So it's the amount of work a pirate can do in a simple way. And the problems in this class, called the pirate class, is actually that if you double the amount of work to do, you need to triple the amount of pirates or something or the other. So no, it's actually polynomial. So basically means that if you would write a program for a Turing machine to solve a kind of problem, it will only need a polynomial number of steps to do its work. And polynomial can still be a long time, just as it was demonstrated with this machine. So there's a different kind of class of problems, and then there's a nice catch to it, namely it can take a guess. So the next circle I'm going to draw actually is a red one, and it stands for NP. Does anybody know what NP stands for? No problems. Yeah, that will be very interesting. Non-polynomial, yes. So that's actually wrong. So the N doesn't stand for non, but it stands for non-deterministic. So what does that mean? So let's take back to the pirate. So for example, a pirate, a problem from the pirate class or the polynomial class is adding two numbers. You can do that in a polynomial number of steps and a bounded number of steps in a very nice fashion. But what the N stands for is non-deterministic. What you can do is you can take a guess and you have to check if your guess is good. So that's actually not non-polynomial, but it's non-deterministically polynomial. So just make a guess, and if you can check that your guess is correct in a polynomial amount of time, so in a fairly easily bounded number of steps, then you are in NP. And I deliberately draw the P inside of the NP, but that actually is an open question. Actually, it's very interesting, so the joke was apt. There's another class, which I will draw now with, for example, green. And it is the hard problems. Hard problems are the problems that are at least as hard in the term of solving it in an amount of time as the MP problems. So these problems aren't easier to solve than the problems in MP. And the intersection of these two clouds is actually MP complete. So what does this mean, all this mumbo-jumbo? Like, you're talking like a mathematician, right? So it actually means there's a certain set of problems which are very interesting because they have the property that if you take an MP problem, non-deterministically polynomial problem, you can reduce it to a problem which is well known. So why would you be interested in that, you would say? Well, the nice fact about that is that all those problems can be reduced. So let's skip this image because it's not very interesting. Let's take an example. An example everybody knows. The problem of determining if there exists an interpretation that's still, what? So this is actually a part of programming. So a Boolean formula is actually just some variables. Let's say you want to make the captain happy. So if there's a pirate, the pirate can be either awake or asleep. He can be singing or fighting or not fighting. So these are all variables which you can answer yes or no or true to false at. And those symbols, you can either be awake or singing or not fighting. And if this expression is true, well, then the captain is happy. So could someone give an example of a state which would make the captain happy? So if a pirate would be awake, the first clause would be true. And if it was not bored, the captain would be happy. That is entirely correct. So it doesn't seem that hard to solve this problem. But in general, this is a problem that is, well, basically the best thing to do is just brute force the crap out of it. Yeah, but this should be about playing games. So why should we talk about Turing machines? Well, Turing wasn't the only one thinking about to formalize mathematics and describing a way to do it. There are a lot of alternatives. One famous alternative is by Church, and he came up with the Lambda calculus. So this is like the father of functional programming. Well, it's where Ruby got its procs and lambdas from. And it actually just is functions all around. It's like it's functions all the way down. And if you would compare Turing machines to assembly, this will be like a higher level language. And the interesting thing is that they're both as powerful. So in a sense, you can take a Turing machine, write a program for it that will calculate all lambda calculus expressions. And vice versa, you could write a lambda calculus function that would simulate a Turing machine. So they are as powerful as each other. So that's an interesting thing. So you can take one thing and can simulate the other and vice versa. And everything on this slide, that will come on this slide, has the same property. So the other thing are flow diagrams. And I put up a picture of Scratch, which seems like a playful or childish maybe programming language. It is actually very powerful. This is as powerful as our Turing machine. It is as powerful as lambda calculus. It can do exactly the same things. you should maybe work harder to describe a program for a Turing machine than in Scratch. But in principle, you can do everything with it. And this is an example which is interesting because, well, I hope one day my daughter will try to make programs in Scratch before she goes on to Ruby, of course. Another part, which is similar, quite similar to the proposition of the Boolean algebra, of the Boolean formula example, is logical programming. So you can imagine that you can do computations with logics if you know how to combine simple formulas into complex ones and do computations by that kind. And this actually, there's a book about this. It's called Understanding Computation. And it's a marvelous book which uses Ruby to simulate these kind of programs and tell you how you can do computations just like the Turing machine example earlier. So if all these kind of things, all these alternatives are as powerful as the hallmark of computation, the Turing machine, why shouldn't we do these kinds of things? So let's do that. But this is still kind of boring, isn't it? It's like, it feels like work. And programming should be fun. So again, a mathematician came up with a brilliant idea, is can we play and do computations? And in fact, you can. So playing should be fun, or computing should be fun, and should be challenging, and should be socializable. No, wait, we're pirates, right? We're gonna cheat the hell out of each other. So no, scratch that. No, so I'm gonna explain a little game to you. It's a simple game. It's played by well, drawing actually things. So we start out with well, let's make a little square. Oops. It should be a black square, so let's change color. So these are dots. You can make bigger dots, and you can make small dots. And well, let's draw some arrows. So we're going to draw red arrows from the dots. Oh, this is nice. So you can draw arrows from one dot to the other dot. And you can also paint them blue. So this is what the mathematician would call a constraint graph. So how would we interpret this? Well, the small dots are actually sinks. And the small dots would like to have at least one pointed at them. The big dots would like to have two pointed at them. And the red arrow will give one to the sink it's pointing at, and the blue arrow gives two. Does that make sense? Great. Well, this is basically the start of the rules of the game. You have such a configuration, and you should make the graphs, the drawing, happy. So is this a happy graph? What do you mean by happy? So that's a good question. This graph is happy if every dot has an inflow, the number of edges, of the weight of the edges, that add up to his wish. So the small dot should have an inflow of 1, which isn't the case, because this little tiny dot isn't pointed at by anyone, which is sad. So this isn't a satisfied graph. Could you make it satisfiable? Just let's add an arrow without drawing the... If I don't draw a dot, it doesn't need an inflow. So this would make the graph happy. Is that clear? Because it's like, if you don't understand the rules of the game, you can't play. So this is important. So what's the object of the game? Because every game should have an object. Well, the object is to switch at least one edge. So I'm going to pick the blue one because it's the only one on this picture, and it's the object to change the orientation without making the graph unhappy. And in this case, it can be done. But if there was another edge of an arrow like this, then the little dot, the lowest dot, is satisfied, so we can alter the direction of the plane and we win. Woohoo! That's great. So I'm looking at a face full of blank stare. Like, why? What is he doing? What's going wrong? So at least it's a game. Let's solve that. It's not a very fun game, but it's a game. So let's explore this game a little bit. I'm not going to ask you to play it, but let's explore it. So let's look at a special kind of configuration. So I'm going to draw a graph, different color, which should be satisfied. And you should tell me why I've drawn that graph. So this is a big dot, which needs 2 to be satisfied. And we have these tiny red arrows. We're getting there eventually. Oops. That point into or out to it. Like so. So why would I draw this? That's exactly right. So to confuse you, no. So this drawing is actually a primitive or a building block of more complex graphs. So, but you can imagine, so this graph isn't satisfied. It needs one more edge pointing in. So imagine that originally all the arrows were pointing in. Then we could safely swip one. So this is actually, you have a choice to make. And by giving it a choice, you can select things to have happened. So this is interesting. I will draw, so this could in a sense be an AND. So only if both of, so let's call the lower one the output or something, and the upper one's the input. Only if both of the inputs are pointing into the dot, the output can switch. So this is basically an AND. So let's draw an OR. So does anybody know how an OR should look like? Me neither. No. So it looks very much similar. As the AND, it only uses different colors. So now the blue arrows add a weight of 2. So if either of the 2 arrows point in, then the red arrow can swap orientations. So this is actually a configuration of OR. And I mentioned the book Understanding Computations, and in this book you get to be told that, well, that all you need to build up complex programs or computers are ANDs and ORs and combinations of them. So there's one slide where I'm going to draw a little bit of an AND and OR configuration which computes something, and in that sense you can play games to compute things. Or maybe I'm not going to do that because it's very tedious. But why should you only focus on that simple game of drawing dots, which is very tedious? Well, the mathematician, just like Alan Turing, created the Turing Machine, which is as powerful as Lambda calculus, or is as powerful as Scratch or flow diagrams. This game is as powerful as a lot of other games. So in that respect, you can use this game to simulate, or actually you can use another game to simulate this game. So for example, who likes sliding block puzzles? I do. So the object of a sliding block puzzle is there's a configuration of blocks, and You have to slide them around to move another piece to a certain location. That's an interesting puzzle to me. It's an interesting game. And you can use sliding blocks to simulate these configurations of inputs and outputs and simulate the switching of edges. And because you can build up a computer in the graph, you can create a sliding block puzzle that can calculate something. And that's actually awesome, at least to me. Thanks for sharing. And not only sliding blocks, there's a host of different points. Who knows the game Tip Over? So Tip Over is like also a puzzle game in which you have a grid, and on that grid there are boxes, or stacks of boxes. And there's a tipper, and the tipper can tip the stack of boxes over, and it will fall horizontally or vertically, and then you can walk on the boxes to another field. So if you look at this picture, there below there is marked start, there's a little red tipper, and all these crates of boxes are of height 2. So you can walk around this grid, but sometimes, for example, if he walks down this path, he has a gap. So you have to make sure that he can tip over crates and walk to the other side. But these configurations are chosen such that they mimic, again, the OR and AND gates which are just drawn. So again, by showing that tip over, that you can use tip over to simulate that silly, stupid game I just drawn and explain to you now, you can show that you can make computations with tip over, which is awesome. And since this is a pirate-themed conference, there's also a game called Plank. The object is to walk on certain struts by laying a plank there, walking over, picking up the plank behind you. It's a fun game to do with your children, and walking along the plank. And again, this image looks very much similar of the sliding blocks puzzle. This is a simulation of the grids of the game. So, what does this tell us? Well, first, never ask a mathematician to talk on a Ruby conference, because he will talk mathematics. Second, Alan Turing was a wonderful man, I think. I never met him. He died tragically, actually, which is an interesting story to tell. Does anybody know how he died? Yeah. So, he died actually. So where to start? He was very much a great fan of fairy tales, and his favorite fairy tale was Snow White. You know, Snow White's the one which get abandoned by her stepmother because she's too beautiful. The stepmother, well, gives her a poisoned apple and she dies, only to have waken up by a prince. Blah blah blah. So you should read the story. So. It was Alan Turing's favorite fairy tale, and he would eventually poison an apple and eat it. But the reason why he did that is very, very sad. So, in my opinion, Alan Turing is a war hero. He helped crack the Enigma code, the code that the Germans used to decipher their communications between their military officers. And he helped crack that code in a very marvelous way. So, at the end of the war, you should expect that Britain would herald him for his work. But unfortunately for Alan Turing, he was a gay, and he was open about it. And he got sentenced for chemical treatment because of his disease, which is very, very sad. And he developed breasts and all sorts of other ailments because of the treatment. So, yeah, he breathed himself of his life, which is very sad, which is very stupid to end with at this moment. Unfortunately, I can't untell the story. But he was a war hero, and he helped liberate, in a sense, everybody in Europe at the end of the World War, the Second World War. So, but what he used to do, he dreamt up this machine. He told us how to program it, and he paved the way for creating a computer which is dear to us every day. And he actually didn't stop there. He dreamed what this machine could do, And he envisioned, playing games on the computer. He wrote extensively about chess, about artificial intelligence, and he set the record straight about what it is to do with programmers. So in that sense, I would like to share this story with you, that the games is just another way of computation, and maybe that's why games are such an interesting thing to do. Are there any questions at this moment? Okay, so the question is, and you understand correctly, if I create a configuration of game elements, and I would simulate that with a computer, or I would play that game, who would be better, the computer or the human? Is that correct? Okay. So, like Alan Turing's machine, computers are very dumb, but they're quick. So in small sample sets, solving a small set which you can visually inspect the problem, humans are usually far better than computers, because computers basically can only do a brute force search. So there's a tipping point, literally, that humans fare much better than computers, and on the other side, computers do better because the problem becomes too complex even for a human to understand. So yes, you can beat a computer for small size problems, but you're definitely going to lose out, because a computer just keeps on calculating, checking, and producing an answer. Other questions? Awkward silent. So I created a Ruby program to play this game. Unfortunately, my mom got sick and eventually died of her illness, which is sad, but she really loved me being here. So this is a bit also for my mother who died. So thank you for your attention, and happy hacking.